A very good morning to all of you, and I hope everybody is fine. And today we'll be talking about time-dependent perturbation. And I always believe that we should always come up with questions. We should raise queries. We must have a stand of curiosity within us. And if we fail to start questioning in science, then certainly the consequences do not become the part of the science. If Einstein would not have raised the question that why can't time be other than that of absolute, we wouldn't have a theory of relativity. We wouldn't have today the well-established theory of special theory of relativity, general theory of relativity. If Einstein and the like of Einstein, who had curiosity to understand the nature, to come up with the questions for whom there was no answer, then the world would not have reached to the level at which we are right now. So it's important, what I believe, for all the students who are doing science, it's important for them to have that stand of curiosity. It is that level of curiosity that is important for a student. And it's the failure of that curiosity that takes us to the next level of understanding. We don't want to be the part of the planet that we have right now. And certainly God has given us a favor. And we must endorse, we must go on questioning and look for the answers to those questions and lead ourselves to the next level of understanding. What was well said by Richard Feynman that the life of a scientist goes like having an onion and doesn't know what's inside the onion, taking the layers of the onion to understand the next layer. It goes on and on. So what I believe is that this state of curiosity should be part of the students. They must come up with the questions which may look so awkward, which might have no answer. It's those questions that advances a society into the future. So let me give some introduction of time-dependent perturbation theory. And as we have almost finished the time-independent perturbation theory till now, so I'll give an overview first, then we will go with the mathematical approach to this time-dependent perturbation theory. So time-dependent perturbation theory, it basically studies these quantum systems which evolve when we subject these systems to the time-varying external influences or the external disturbances. So you have a system, you subject that system to an external perturbation, and that external perturbation is assumed to be dependent on time. And this gives rise to what's called as time-dependent perturbation theory. The physical intuition of this theory is that it basically helps us to understand the transitions that take place from one level to another level. It certainly guides us that under which circumstances your quantum states, you can have a transition in the quantum states when you are acting upon an external disturbance to your system. And as I said, the key concept for this this theory is, it's basically a small time varying change. That's why it falls in the context of perturbation. And, and how does this, this small time varying disturbance affects your system's energy levels and probabilities over that short span of time? So this is how the key concept is basically exaggerated in those quantum systems in which these time-dependent perturbations are assumed. And we can think of an atom in an oscillating electric field. You have an atom and you subject an atom to an external electric field. And this field can undergo transition. You can have transition between energy levels. So this basically models the situations where we talk about the absorption of energy or the emission of the energy. So the problem of subjecting your atom to an external oscillating electric field is an example of time-dependent perturbation. We can also think in terms of magnetic resonance, and what we have is nuclear magnetic resonance, what we call as, maybe in modern technological point of view, we have MRIs as the technological replica of this nuclear magnetic resonance, where we can see the image of the body of a human being and trace out if there is any problem in the body. So in NMR, what we have a time-varying magnetic field. What we do is we subject the system to the varying magnetic field, and it perturbs the spin states of these nuclear states, and then enables a transition, the nuclear transitions within these atoms. Laser-driven transitions. You can induce the transition in lasers. I mean, when you have a laser, we understand what a laser is, where you can have the coherence of energy, you can super amplify the energy that you are subjecting to a laser. So we can induce the transitions using these lasers, and we can have a crucial understanding in spectroscopy, and we can understand how to control the quantum systems. So this is again a problem of time-dependent perturbation that certainly guide us how to manipulate the technology for application purposes and for understanding purposes. Quantum computing, as you know that we are now in a world where we have two classifications. We have the quantum computers on one side, on another side we have the conventional classical computers, and majority of things that are happening in the globe, they're happening through these classical computers. And classical computers are working on the classical principles, the classical laws of physics. You have only two states in classical computers in terms of the operations that will execute, where gates, and all of these operations can be executed in terms of these binary states, what we call as 0 and 1. But on the other side of the story, we have the quantum computer, and quantum computer works on the principles of quantum mechanics. And here in this domain, your system can probably work in a superposition state. You don't have only a dual state that you have in classical computers. You have an infinite number of states that can be made operational. And when we think about the calculations that can be executed using quantum computers, that has no match in a classical computer. So perturbation, the time-dependent perturbation, it certainly helps us to understand how these perturbations can be used to manipulate these quantum bits that we have in these quantum computers, and to have those transitions that that can take place in the gates, what we call as quantum gates. And we have examples of quantum gates, like we have Hadamard gate, and there are a range of basic quantum gates. By designing those gates, we can develop a quantum computer. Even though the actions that can be perceived using these quantum computers, they cannot replace the jobs that are being done by the classical computers, but they have tremendous possibilities, they have tremendous potentialities to solve the problems of mankind, to solve the problems of climate change, to solve the problems of complex molecules, to solve the problems of designing more accurate materials, and many more things that can be done. So perturbation, the time-dependent perturbation, has a strong role to understand the quantum computing. In the similar fashion, it has applications in spectroscopy. It certainly does allow us to understand the transition probabilities, and these transition probabilities can lead us to the predictions of spectral lines and the intensities. It has applications in semiconductor physics. The time-dependent perturbation models the response of an electron. You have an electron moving in a periodic potential of a semiconductor, and we can understand that how an electron responds when you are acting upon these electrons to a time-varying fields. And this is what becomes the basis of aiding or designing our electronic devices. So to conclude this introduction, we can say that the time-dependent perturbation theory is a powerful tool. It's a very strong tool for predicting the behavior of the system. And the behavior of our system, that you are subjecting your system to a time-varying environment without doing a detailed kind of mathematics. So this is how we can introduce ourselves to what's called as time-dependent perturbation. So now let's go and develop a mathematical model for this time-dependent perturbation. So today we'll be in a position to talk about this time-dependent perturbation. So we'll be using some symbols, some states. Now let's define those symbols first and go on developing the theory of time-dependent perturbation. So as we understand now what time-dependent perturbation means, what we have to do is we have to calculate a Hamiltonian that contains an unperturbed Hamiltonian and a Hamiltonian that acts as a time-varying disturbance to the system. So if I choose H as my Hamiltonian, which gives us the total energy of the system as we understand, then this Hamiltonian can be written as H0 and HP. Now this H0 is the Hamiltonian of the unperturbed system, which is exactly calculable. We understand how to calculate this H0, and then you have a perturbation, and this perturbation is a small time varying disturbance that's acting on our system. So to start with, we will choose an eigenstate. Say, if I choose an eigenstate psi n of t, and this eigenstate, I can write down this eigenstate as a superposition and make it dependent to So a coefficient, say a n of t. This coefficient is dependent on time. Then I will take a time independent state, say psi n naught, and then I'll write down an exponential function e to the power of minus I e n of t. So this is my state vector, this is my eigenfunction, it's dependent on time, and I write this eigenfunction as a superposition of the states, including a time-dependent coefficient a n of t, and an eigenstate which is time-independent belonging to my unperturbed Hamiltonian, and an exponential function that's dependent on the energy and the time. So this is my eigenstate as I choose it, the solution of the Schrodinger's wave equation. So if I write down the Schrodinger's equation, I can write down this is I h bar dou by dou t of psi n of t. The ket of psi n of t is equal to the Hamiltonian operator and psi n of t. So this is my Schrodinger's time-dependent equation, and we can easily see that what we have to do is to evaluate this ket of sine of t. And if this sine n of t is already defined, all we have to do is to differentiate this eigenfunction, and once we differentiate it, we would like to use the result in the result that we obtain in the Schrodinger's equation. So for that, what I will have to do is I will have to calculate this the derivative of this eigenstate. So if I do that, so that is dou by dou t of for the ket of sine of t, what I have is I have psi n of t as sigma a n of t, then I have psi n naught, the ket of psi n naught, and e to the power of minus I e n of t. So what I'm doing is I'm differentiating this eigenfunction. So once I differentiate this function, the result that I will obtain, I will use that result in the Schrodinger's equation, and then from there we are going to proceed. So if I have to differentiate it, so I keep this as constant, this is a constant, so I would like to differentiate the exponential part first. So what I will have inside is sigma. Okay, the differentiation of the exponential is an exponential, but you will have to take the derivative of the internal derivative of the exponent that you have. I think here I have committed a mistake because it has to be divided by h bar. So you define your exponential as en divided by h bar. Okay, so now I will be writing this exponential function as is, but I have to take the internal derivative of this exponential. So internal derivative will give me minus I en by h bar, and your exponential function will remain as is, e to the power of minus I en of t by h bar. And then plus, okay, what else will remain there? En of t is there, and the ket of psi n naught is there. So this is my first term. The second term, for the second term, I will have to keep this exponential function as it's, and I will have to differentiate the time-dependent coefficient. So for that, what I will have plus sigma for a n of t. I will use a prime. This prime is telling me that it has been differentiated with respect to the time. So this a prime of t, a n prime of t is nothing but d by dt of a n of t. So this point should be noted here. And since I have taken the derivative of this coefficient, I would like to write down the next part, psi n of naught, and e to the power of minus iota e n t by h bar. Okay, these are the results that we have obtained when we have differentiated our eigenstate with respect to the time. And one thing is clear, that I can use the value of this eigenfunction in the Schrodinger's equation. So in the left-hand side, I have to use the time derivative of this eigenstate, and in the right-hand side, I have to use the state as itself. And for h, I will be using h naught plus h perturbation. So proceeding from here, what's going to happen? So I'll have to multiply, basically. I will have to multiply this thing with I h bar. So when I multiply this thing with I h bar, I just scatter will give me minus 1. Minus minus will be plus. So I will have sigma, this h bar and h bar for this term will cancel. So what I'll get, I'll get sigma En. En will be there, and then you will have psi n naught, then you will have e to the power of minus iota En of t by h bar. This will be our first term. H bar and h bar is gone. Now that I h bar has to be multiplied to this as well. That I h bar has to be multiplied to this as well. So here, what we will have plus sigma I h bar, and then I'll have a n prime of t and psi n naught and e to the power of minus iota En of t by h bar. So this is going to be our left-hand side of the Schrodinger's equation. And in the right-hand side, what we have h times the eigenstate. So let me write down this again. So what should I do? I should write down this is sigma, and here you have En, then you have psi n naught e to the power of minus iota En of t by h bar. This is the first term. The next term is sigma, then you have I h bar is over here, then you have a n of prime of t, then you have psi n naught, the cat of psi n naught, and then you have e to the power of minus iota En of t by h bar. This is equal to. Now this is equal to h. For h, what I have h naught plus hp. And this is to be multiplied by the eigenfunction that we have. So what's that? That is sigma a n of t, then psi n naught, then e to the power of minus iota En of t. Right. So this is my equation. Now we can see that we can separate out these two terms. We can multiply with h naught to this whole, and we can multiply this perturbation Hamiltonian to this whole thing. So what we'll be left with? We'll be left with h naught sigma a n of t psi n naught, then e to the power of minus iota En of t by h bar. So you will have h naught term, and plus you will have hp, the perturbation term, and the same sigma a n times t, then you'll have psi n naught e to the power of minus iota En T by H bar. Now this is my equation. You have the left-hand side of the equation and you have the right-hand side of the equation. And let me define, let me multiply this, whole equation from the left side using another basis in the same Hilbert space as the draw of psi m naught. So what am I going to do is I'm going to multiply from left. I will multiply from left this equation by the draw psi m naught. So for that, what we'll be coming up with? Let's do that. So we will have sigma, then we will have En and psi n naught. Okay, I should not write it like this. I should write the cat of psi m naught and psi n naught, then a n of t, then e to the power of minus iota e n t by h bar. This will be term number one. The term number two, we have sigma I h bar, and then we have sigma I h bar a n prime t, and we have a n prime t, and then cat of psi m naught and psi n naught e to the power of minus iota e n t by h bar. So this is our left hand side, and our right hand side we will have sigma, you will have the cat of psi m naught and then h naught psi n naught, and you will have a n of t there, then e to the power of minus iota e n of t by h bar. So this will be the third term on the right hand side, and the last term that we will have plus sigma a n of t and psi m h perturbation psi n and e to the power of minus iota e n t by h bar. So this is how it goes. Now what we have is we have four terms, and in the left hand side here we have the term En psi m naught psi n naught a n of t e to the power of minus iota e n of t, right? And in the right hand side, if we see here, for the cat of psi n naught acting on the unperturbed Hamiltonian, will give me En naught. So we can immediately see that this term and this term, these two terms can be exactly cancelled. So you can cancel this term with this term, and what you'll be left with, this term in the left hand side, and you'll be left with this term on the right hand side. So what you will have, since we are acting upon by the state psi m naught, and this psi m naught, psi n naught will only exist if m is equal to n. For m not equal to n, because this, if I write down the Kronecker delta for this, delta mn, this delta mn is going to be 1 for m is equal to n, and this delta mn is going to be 0 for m not equal to n. So if I do that, if I boil down this term to the state m equal to n, I can replace en in the exponential by en. So I can do that. So what should I write? I should write then sigma an prime of t. Now an prime of t is the time derivative of the time dependent coefficient that we have here. And then we will have e to the power of minus iota em of t by h bar. This will be one term. In the right hand side, I can write down, I have sigma, then I have an of t, and I have the expectation value, psi n naught, hp and psi n naught, and this is multiplied by exponential e to the power of minus iota en of t by h bar. Now we can easily see here, we can take this summation out because we have chosen a situation where n is equal to n. So we have replaced our n by n in the left hand side, and we can be writing this derivative of the time dependent coefficient, and we can translate this exponential function on the right hand side of this equation. So when we translate this exponential function on the right hand side, it will go down. When it goes down, in order to bring it into the numerator, its negative sign will convert into the positive sign. So what will be the result that will be obtained here is we will have an prime of t is equal to sigma. Then you have an of t, and you have the expectation. I should write the short form of this expectation as hp n, and then we will have e to the power. I think iota will be out. Inside I will have em minus en times t by h bar. Okay, so we can, as we know from Planck's equation, as we know that that h cross omega is em minus en. It has to be naught. I might have committed that mistake. You can fix that yourself. So omega will be em minus en by h. Okay, I don't need this. I need this. Okay, come on. So this has to be em minus en by h bar. So in my equation, I have for exponential this em minus en divided by h bar. I can replace it by omega, and where omega is the angular frequency. So we can write down this an prime of t is equal to sigma an of t and hp mn and e to the power of I omega. For omega I should use mn of t. So to keep the track of the symbols that we have used, so it's em minus en, so let's use it as mn. So we have an equation, we have a generalized equation for the time-dependent coefficient an of t, the derivative of an of t. Now if I think of expanding these coefficients, I mean, if I use for an of t, I can use an, for n I'll be using, say, 0, a0 of t plus lambda a1 of t plus lambda squared a2 of t plus so on and so forth. And similarly, this is for the prime one, which has the time derivative associated with it. So here I have the prime one, and I can think the expansion of an of t as A naught of t plus lambda A1 of t plus lambda square A2 of t plus so on and so forth. And for this HPN, I'll be using, I will multiply this HPN by this lambda. This lambda happens to be extremely small, so we'll be introducing lambda for this HPN. And use these expansions in our equation. What we'll come up with is we'll have A naught of t prime plus A1 lambda A1 of t prime plus lambda square A2 of t plus so on and so forth. This will be our left hand side. In the right hand side, we'll have that sigma, and then for A, we will have A naught of t, then plus lambda A1 of t, and plus lambda square A2 of t. And this will be multiplied by lambda h, p, and n. And then you will have the exponential e to the power of iota omega mn of t by h bar. Now we have the expansion, and this equation has to be true when each and every coefficient of lambda square are equal to 0. And we can see here, we will have a track here. For A1, I will have here A1. For A1, I will have lambda square, because A1 will lead to lambda square. A naught t will lead to lambda. So the first term will have no comparison. And this first term will not take into consideration for the time being. So what we will say is, if we compare the coefficient of lambda, that will give us first order correction. So for lambda, what we will have? For lambda, we will have A1 of t. So it will be A1 prime of t is equal to sigma. Here we have lambda, here we will have A naught of t, because this will be multiplied by this lambda h, p, and n. So what we'll have A naught of t, then h, p, and n, then e to the power of iota omega m n t by h bar. So we can see, we can do it ourselves, we can understand. If we got to correlate the A primes with A's without the primes, here we will have one order greater than that of the order of the coefficients of the time that are in the sigma over here. So this is going to give us the correction. This is going to give us the first order correction to our Hamiltonian, and the same thing can go on for second order if we compare the coefficients of lambda square. And what I believe is the main point of contention should be the first order correction. Now let's go with first order correction, and we can see that to make this equation mathematically true, we choose this A naught of t equal to 1. So to make it mathematically correct, what we do is we choose this A naught of t equal to 1. So what we are left with, A1 prime of t is equal to sigma, the expectation of psi m h P psi n e to the power of I omega m n of t. Now, here what we have the amplitude. We have the amplitude A1, and if we have the amplitude, we can calculate the probability density. So how we can calculate the probability density? The probability density, if you have to calculate the probability density from here, what I'll take more of A1, it has to be prime here because it is the derivative of A1 of t. So I will take the more of square of this A1 prime. So what will I get out of here is I will be getting the probability density, and that probability density will be A1 prime of t, its mod whole square. So what should we do? We should bring all that sigma and psi m h p psi n, they have to be knots, and we have to take the square of this, and we have to take the square of e to the power of I omega m n t. Okay, and we can understand that when we take the mod of square, if we go back to the wave function, we take what it means to have probability density is you have an eigenstate, you take its complex conjugate, and you multiply the two. When you multiply the two, the complex part goes equal to 1. So that's what's going to happen here in our case. This magnitude of e to the power of I omega n of t, it will be multiplied to the negative of e to the power of minus I omega n n t, and that will lead us to a value equal to 1. So the probability density that we will have here, that will be psi m naught, the draw of psi m naught, you will have the bracket, you will have the Dirac notation of this perturbation, psi n naught whole square will give us probability density. So today we'll stop here, and in the next lecture we will proceed from here to calculate the transition probability, because in the beginning of this lecture I talked about the applications of perturbation, because perturbation leads us to understand why and how the transition takes place from one state to another state when you are applying an external disturbance to the system, and how your system leads to have a transition from one quantum state to another quantum state. I probably think that we will do that in the next lecture, in the next video. So, a very good afternoon to all of you, and in continuation to our previous demonstration of the theoretical demonstration of time-dependent perturbation theory, we would like to proceed on, and we would like to incorporate some of the physical quantities in our perturbation formalism that we have developed till now. So what we have obtained in our last expression is we have the first order perturbation amplitude an of t prime. This is equivalent to sigma the Dirac psi m h p psi n. This is our bracket for the perturbation term, and this is multiplied by e to the power of I omega m n t. So this was the result that we have obtained, and we would like to proceed from here in terms of this first order correction, in form of the perturbation that is introduced to a system of whose ideal Hamiltonian is exactly solvable. So what we do here is we would like to go for the first thing, that is we will subject our problem to what is called as constant perturbation. So when we say constant perturbation, then what we assume here is we assume that this bracket it's constant of time. It varies constantly in the limit of, say, from 0 to t. And this constant perturbation is not applicable for the time interval which is greater than, say, t dash is greater than t, or t dash is less than 0. So this should not be taken as the division. This is the multiplied part of this bracket times e to the power of iota omega m n t. So how do we define the constant perturbation? We define constant perturbation by assuming that the bracket that we have it's constant in time, at least in an interval from 0 to t. If that's the case, and if we want to calculate the an of t, it's not, I would like to call it, let's go with an, this is a1 prime. So in doing so, what we will have, we will define it as, say, a1 of t will be integral from 0 to t, and inside what we will have psi n h p and psi, it has to be, do I take it as psi n and psi n e to the power of I omega m and t. And we have already we are already knowing about e to the power, we know that this omega mn is omega, and it's nothing but em minus en by t. Okay, so what we can do here is we can get this bracket out of the integration. So we will have psi n hp and psi n, and the integral from 0 to t e to the power of I omega m n t. I should use here t dash because we have to give the limits, and dt dash. Okay, so here I should put t dash and multiply it by dt dash. So a1 of t, we are calculating a1 of t, and the bracket is out, the matrix element is out, and all we have to do is to integrate this exponential function. Now, so proceeding from here, what we will have a1 of t is, okay, you have this matrix element, this is psi n is is it N? Yeah, it's M. And HP and psi n is out. And on integrating, you will have the exponential function as it's e to the power of I omega m n t dash divided by the internal derivative of the exponent will give us I omega m n, and you will have the limits running from 0 to t. So I can go with the next step over here. This is a1 of t will be the same thing, psi m hp and psi n. I think I have missed something important. And what was that? It was basically multiplied by I h bar, so it has to be 1 by I h cross. So I should write down here, divide by I h cross. So what will we write here? We have I h cross, and then we will have this I omega mn. Okay, so here we will give the limits. So what we'll come up with is e to the power of I omega mn t. This will be the upper limit, and the lower limit will be e to the power of 0. So here we can see this iota square will give us -1, and the result that we'll obtain here for a1 of t, so this e to the power of 0 will give us 1. So what we'll be left with is a1 of t will be psi m hp and psi n by, so minus should be out because we had iota square, and in the denominator we'll have h cross omega mn, and it's to be multiplied by e to the power of I omega mn t, then we have -1. Now let us resolve this this function using a limit. So if I have limit omega mn t tending to 0, then the value of this will be e to the power of I omega mn of t minus 1. The value of this function will be 2i. It will be 2i sine of omega mn t divided by 2. So we can use the result of this bracketed term in our expression. So for this bracketed term, we are going to use 2i sine omega mn t by 2. And we'll do that. Okay, what we'll get after that? We'll get a1 of t is, you have a negative sign, then you have psi m, you have hp, you have psi n, divide by h cross omega mn, and this will be multiplied by 2i. So I would like to write down this 2i here. So this is 2i, then sine of omega mn t divided by 2. All right, so this will be my probability. This will be my amplitude that I have been calculating for a system where I'm subjecting my system to what's called as the constant perturbation. And to proceed from here, if we want to calculate the transition probability, calculating the transition probability is what we generally call as Fermi golden rule. So How can we define the transition probability? We can define transition probability using the amplitude for this first order correction that we have. This, if I assume that this transition probability is omega, and this omega can be defined as what's transition probability? You define it as transition, and as transition over a unit time. So if I have to write down this transition, it will be 1 by t integral, and the limit of this integration will move from minus infinity to plus infinity, and you will have a1 of t. You will have the scale of its amplitude, okay, and you define a term known as energy density. I choose that energy density as a rho of n, and you integrate this thing over an energy range, say DEN. What basically is happening is you are calculating the transition. Suppose you have two levels. You are calculating the transition from say E to E plus DEN. So transition probability, if you have to calculate the transition probability, you calculate it by making a transition of your particle from one state to another state. So we can formulate this transition as, because we define the transition probability as the integral that we have defined it here over the energy from E to E plus dN per unit time t. Now this A1 of t is already calculated, so we can use the value of A1t here in this integral to calculate basically this transition probability, what is generally known as Fermi golden rule. So our omega in this case will be 1 by t integral minus infinity to infinity, and for a1 of t we have a result. What's that? We have a result of 2i. I should check that. What was that result? So what we have, maybe I forgot something. Okay, what's that? Okay, that's fine. This thing is also fine. Okay, so this is 2i, yeah. So 2i is there. So we will have 2i here, then we will have psi n hp and psi n. Okay, we'll have the square of this, we'll have the square of this, okay, and we'll have the square of h cross square and omega mn square, and then you will have e to the power. Now there is well, if you check that, okay, so now here you will have e I omega mn t, and you will have a rho of n, and you will have square of this. I mean, the square of this term will be there, and rho of n and dE of n. This is how it will look like. Okay, so if we assume that the time interval is extremely large, we can take this bracket term, the square of the bracketed term, we can get it out. This 2i will give me, this will give me 4i square. So 4i square will give me, because I have to take the complex conjugate. So this will give me plus terms. So here I will have 4 by t, and I can get this matrix out. I can get this bracket out, psi n, hp, and psi n, assuming the time interval is extremely large, this whole square, divide by h bar square omega mn square. So inside the integral, which is from minus infinity to infinity, I think here I have committed the mistake. This is already calculated as, what is this calculated as? I have calculated it as sine square omega mn t by 2. This is it. And this is where I was committing the mistake. There, we have already calculated this in the previous integral. So what we have, here we have the square. Here we have the square of sine square omega mn t by 2. And then we have the energy density that we have inculcated over here as rho of n, and then you will have here dE of n. So rho of n will be out of integration. So here you will have dE n. Now what we can do here is we can write down this dE n, because we know that En is h cross omega mn. So d En will be h cross d omega mn. So for den we can use h cross d omega mn. So when I do that, let me look at that equation. So I'll be writing this equation again because I'm calculating the transition probability. So what I'll have 4 by t. I'll have 4 by t. This omega will be 4 by t, and your bracket of psi m hp and psi n whole square. This will be out, and rho of n will be out. This is divided by h bar square omega mn square. And then you will have an integral from minus infinity to infinity. And I can write here sine square omega mn by 2. And this will be multiplied by h cross d omega mn. So we have converted this integration in terms of omega mn. And you can see here immediately this h bar, this h cross, and this square will cancel. And I can introduce omega mn square into my integral, because then I can use a standard result of the integration to calculate this transition probability. So what can I do? I can write down this transition probability as omega. Okay, then we have what we have. We have the matrix element of psi m, then we have hp, then we have psi n. This is whole square. Okay, this is here. Then we have the integral minus infinity to infinity. Now I can write sine square omega mn t divided by 2 divided by omega mn by 2 whole square d omega mn. And here, as you can see, that we can use the result of a standard integration. If you have an integral running from minus infinity to plus infinity, sine square x by x dx, the result of this integration will be 2 pi t. So for this integral, I will directly use the value, and I will be getting my final expression. I think here I'm missing the h bar because one h cross was cancelled, but still one h cross was left over here. So the result of this integration will give us 2 pi t, and I forgot to write t here because the integration starts by 1 by t. I mean, when we define this transition probability, it starts by defining per unit time. So per unit time is over here, and this per unit time that we have, we're writing this transition probability as 1 by t. Okay, that's fine. Then you will have psi n hp and psi n whole square times. So instead of all this integration, we have 2 pi t, and you have h bar here. And you can see this t and t will cancel, and we will get we will get the transition probability. So what will be the transition probability? Omega is 2 pi by h cross, and the square of the bracket psi n hp, and then psi n is the square of this, and this is to be multiplied by rho of n. So this equation that we have obtained over here, this is what is called as Fermi golden rule. It's called as Fermi golden rule. And it gives us the measure of the transition. It gives us the measure of the transition that can take place from one quantum state to another quantum state. And what we can do here is we can, if we plot the two functions, the function that we have, like sine square omega m t by 2 versus omega mn. When we plot this kind of thing, what we obtain a curve like this. And our y-axis is something like sine square omega mnt by 2, and the x-axis of this plot is omega mn. And what is the point of importance over here is what we see here when we calculate the probability density, we are getting the resonances, and you have the central peak of resonance. And this graph is somehow matching with single slit diffraction, which is basically the consequence of interference. It's the result of the maximums that you have, is the result of those constructive interferences that are taking place, and you have a resonance. You have a huge peak at the center of this graph. And this graph is certainly directly giving us an evidence that there is a transition probability, and the probability of transition having for a quantum state to go from one quantum state to another quantum state is large at the center of this graph. So this is how the probability density, or I should say the Fermi golden rule, dictates us theoretically that how does the transition take place in those systems. When you are subjecting your system to an external perturbation, what is important is that your external perturbation must be dependent on time, and that perturbation should act for a very small interval of time. So when such a thing happens, we obtain a result like this that gives us the measure of the transition probability for a system to move from one quantum state to another quantum state. So with this, I would like to stop here, and after this, we'll be looking for more applications of time-dependent perturbation. Thank you.